we have seen different cases of standard second order control system and has also discussed different parameters which are important for determining the performance of second order control system. But so far we have discussed only the second case, which is the case of underdamped oscillations. The other cases are still remaining. So let us first consider the case 1 when the value of zeta is equal to 0. The unit step response can be simplified by putting the value of zeta, which is equal to 0. The same way we can find the value of theta and damped frequency by simply putting the value of zeta in different equations. By doing so, we will get the output response to be equal to 1 minus sine damped frequency multiplied by time t plus theta, where theta will come to be equal to pi by 2 and damped frequency is equal to natural frequency. An approximate output profile is also shown on the screen. Now let us cover the parameters and see if all the parameters are defined for this case or not. The first parameter is rise time. The definition which you are seeing on the screen is actually of underdamped oscillation, which we saw in the last lecture. Here you can see, as per the definition, it is very important to have the desired value of the output, and the desired value is nothing but the steady state value of the output. However, in this case, the output is having perfect oscillations. That is the reason the output will not have any steady state value, and for the same reason, rise time for this case is not defined. The second parameter is peak time. It is a time required for the response to reach the first peak of the output. Here, the terminology of overshoot and undershoot are not valid. The reason is again the same. Since we are not having a steady state value, we cannot define overshoot and undershoot, as overshoots are the region of the output which lies above the steady state value. But here in this case, we don't have any steady state value. That's why overshoot and undershoot are not defined here. The peak will be simply referred as the maxima and the valley will simply be called as minima. These cannot be referred as overshoot and undershoot. We can find the peak time formula in this case the same way we have derived the equation of peak time for the case of underdamped oscillations. We are having the output equation in time domain to be equal to 1 minus sine damped frequency multiplied by time t plus theta. We can also put the value of theta in this equation, which is pi by 2, and as per the standard trigonometric identity, we know sine pi by 2 plus theta is actually equal to cos theta. And we also know the damped frequency is equal to natural frequency. By applying all these things, we will get the output to be equal to 1 minus cos natural frequency multiplied by time t. Now, for the peak time, our first step should be to differentiate the output equation so that we will get the instant of time which are having maxima and minima values. By following the same procedure as we have done for the underdamped case, we will get the formula for peak time to be equal to pi divided by damped frequency or natural frequency, as both are same in this case. Similarly, for different time instants at which there is maxima, the time is equal to n pi divided by damped frequency, where n is an odd natural number, whereas for minima, n should be an even natural number. Peak overshoot is also not defined, as here also the definition is dependent upon the steady state value. And for the same reason, delay time and settling time are not defined, as both these parameters are particularly defined with respect to the final value or the steady state value. There is no time constant as well, because the time constant analogically represents the decay of oscillations, but here oscillations are not decaying at all. That's why the time constant is also not defined here. So we have covered the case 1, which is quite simple, because except the peak time, none of the other parameters is actually defined for this case. Now let us consider the third case, which is the case of critically damped oscillations. We have derived the output equation for the case of underdamped oscillations, but unfortunately it is not valid here. We have to derive it again. We can easily find the value of Laplace transform of the output by putting the value of Laplace transform of the input multiplied by transfer function of the system. Now we can simplify this equation further by putting the value of zeta equal to 1. After factorizing it with partial fraction method and taking the inverse Laplace transform, we will get the output equation in time domain to be equal to 1 minus Euler's number raised to the exponential minus natural frequency multiplied by time t minus natural frequency multiplied by time t multiplied by Euler's Euler's number raised to the exponential minus natural frequency multiplied by time t, the whole being multiplied by unit step signal. Now, here I am going to tell you a very important point. See, there can be different ways by which you can represent the same output, like the two equations which are shown on the screen actually represent the same thing. But I have not used any of these two forms. I have given you the equation of output along with the output profile, where you can clearly see the output is meant only for positive time values. But in subjective exams where you are supposed to write the whole solution, there I recommend you to write your equations in the second form, because if you have to find the equation of peak time, then it may be little bit complicated for you to differentiate the first equation. So it will be much better if you write the equation of output by using the second form. For teaching purpose only I am using the third form, but it is not actually a recommended way of writing the solutions in exams. By putting the value of zeta equal to 1, we can find the value of theta as well as damped frequency, which will both come out to be equal to 0. An approximate output profile is also shown on the screen for the unit step response for the case 3. The rise time definition is slightly different from the definition which we have seen in the case of underdamped oscillations. The only difference comes in the percentage values. Here, it is the time required for the response to reach from 5% to 95% of the desired value of the output at the very first instant. You should not be expecting formulas in this case. If any question comes from these cases, it will be much better if you manually solve the problem rather than being dependent on the formulas. I have derived the formula which are exact and accurate in nature, but the formula which uses approximated equations and are not accurate, I have written them directly without deriving them. You should not give too much dependency on these type of approximate formulas. Peak time is not defined because, as you can see in the output profile also, there are no overshoot or undershoot. And for the same reason, peak overshoot parameter is also not defined in this case. Delay time is the time required for the response to reach 50% of the final value in the first attempt. The approximate formula is equal to 0.7 divided by natural frequency. Settling time is defined with the same definition, however, the formula differs slightly. For 2% tolerance band, the formula is 6 divided by zeta into natural frequency, zeta being equal to 1. However, in the case of underdamped oscillations, the formula was 4 divided by zeta into natural frequency. Again, these are approximate formulas. There may be questions where you have to find the answer by solving the output by first manually finding the output equation in time domain, then finding the time at which it reaches 98% of the final value, rather than directly applying these formulas. The time constant is not defined here as there are no oscillations at all. So we have covered 3 cases. The only case remaining is the case of overdamped oscillations. Here again, we first need to find the output equation in time domain. But here, I will be finding a general equation rather than the exact expression. We can find the Laplace transform of the output easily and can also factorize it easily. After taking the inverse Laplace transform, the output will come out in a form 1 plus a Euler's number raised to the exponential s1 multiplied by time t plus b multiplied by Euler's number raised to the exponential s2 multiplied by time t. Here a and b are constant, which in real scenario you have to find the values by using the partial fraction method or Heaviside theorem, and s1 and s2 are the poles of the system. We also have two equations which are related to parameter zeta. One is of theta, which is equal to cos inverse of zeta, and the other is damped frequency, which is equal to natural frequency multiplied by under root of 1 minus zeta square. Both these equations are invalid here. We can find the value of theta, which will come out to be equal to 0, but the equation is not valid here. There is no relation between the parameter zeta and the theta. We can find the value of theta from the graph only. Now, if you observe properly, you will realize the output profile of the third and fourth case look approximately the same. And interestingly, the parameters which are defined for the third case are the only parameters which are defined for fourth case. This point may be easy for you to remember as the output profile in both the cases look approximately the same. So, as we saw in the previous case, peak time, peak overshoot and time constant were not defined, which are not defined here also. The first parameter is rise time, which is defined with slight difference in the definition which we have seen for the case of critically damped oscillations. The only difference comes in the value of percentage. The rise time is the time needed for the response to reach from 10% to 90% of the desired value of the output at the very first instant. Delay time and settling time are having the same definitions as what we have seen in the case of critically damped oscillations. Now we have seen all the 4 cases and have discussed which parameters are defined for different cases, but still our study regarding the second order system is not complete. In the beginning only, I told you that as an undergraduate level student, you are supposed to know how to solve the standard form as well as the form of second order control systems in which there is one pole. But so far we have discussed only standard form. Now we are going to discuss the second form where there is one pole in the transfer function of the second order control system. Previously we have seen different cases. We have also located the different poles and have also classified them with their names. But all these things are valid only for second order control system which are present in standard form. This nomenclature, which is undamped oscillations, underdamped oscillations, critically damped oscillations and overdamped oscillations, are not valid for this case where there is a one pole in the transfer function, and as such, since they are not named, there is no meaning of different cases also. We have also seen the location of poles as well as an approximate output profile in different cases. The reason why we do not name these cases in this form is quite simple. Actually, the response in the standard form was dependent only on the location of the poles, but here, the location of 0 will also determine the behavior of the system. The 0 can have any of these locations which are denoted by the positions 1, 2, 3, 4, 5. The 0 could be present right hand side of the imaginary axis or left hand side of it. It can be present on the right hand side of the poles or the left hand side. All these things actually determines what type of output profile the system will have, and that's why the output profile which we have seen in the standard form is also not valid here. That's why the nomenclature is not used in the case when we are dealing with a second order control system which has a 0 also. However, the location of the poles will look exactly the same. The reason being very simple, as the denominator has not changed at all. It is exactly the same as it was in the standard form. Now let us see the definition of different parameters which are valid for second order control systems consisting of a 0. The rise time is the time needed for the response to reach from 10% to 90% of the desired value of the output at the very first instant. Peak time, it is the time required for the response to reach the first peak of the output. Few of you may have a doubt, what if the first maxima is not a global maxima? In that case also, you need not to think that much, you have to stick with the definition. As it says we have to consider the first maxima, then everywhere we have to find the time instant at which the output reaches its first maxima, irrespective of whether it is a global maxima or not. The maximum positive deviation of the output with respect to its desired steady state value is known as maximum overshoot. These parameters are defined generally, but it is not necessary that you will get peak overshoot in every case. It may be possible there is no steady state value. The first step in finding these parameters is to determine whether the output is actually having a steady state value or not. Delay time is the time required for the response to reach 50% of the final value in first attempt. Final value of the output, desired value of the output, steady state value of the output, all are same thing. Settling time is the time required for the response to reach and stay within a specified 2% tolerance band of its final value. The time constant is not a universally defined parameter for second order control systems. Sometimes it is defined and sometimes it is not. But remember, it is analogically defined, which represents the decay of oscillations. There are no formulas here. You have to manually derive the equation of output in time domain and then proceed afterwards to find different parameters. If you are trying to search formulas, then also you will get approximate formulas, and if you are dependent on them too much, then probably you will get wrong answers in the exam. Try to solve them manually. Many times you have to use the concept of the first unit to determine the time constant. For example, you have studied the topic dominant pole concept. If there are two factors in a second order control system and one pole is significantly smaller than the other, then you can use dominant pole concept and can determine the approximate time constant of that system. The first unit of any subject is quite easy, but actually it is the most important as well, as the topics of the first unit are generally used everywhere in the later units also.